Hello, everyone. We're back with notebook page 3. And if you want to pause and get the title card here, you can do that. But we're going to be talking about experimental psychology. We're going to finally get into experiments and how they work. So, depending on what science courses you've taken, this might be a rehash of some things, but this is what a lot of the FRQs will want to know. And you'll need this information to answer those effectively, as well as some multiple choice on the AP test. So this is a really important foundation that you'll need for the course. So let's go ahead and start with experiments. And experiments are required in any science to have valid results. So we need to make sure that the results are valid, that we're not just making things up, that we can, with our data, know that it's real and that it's true. They're critical in psychology as much as biology and physics and anything else. So our theories have to be testable. We have to form a hypothesis around it, around what can be tested. So if we can't have verification via experiment or through some type of logical proof, then it's just speculation. We're vulnerable to bias, which is a predisposition to a particular set of views that we're trying to find something, so we'll just believe that it's true. So let's say we have a hypothesis that there's a rise in anxiety in students the week of midterms. And for the theory to be valid, we have to be able to have an experiment. We have to be able to repeat it by ourselves and by other scientists. And so operational definitions are something that's needed. And what this means is just identifying and defining what this is. Like, what is anxiety? That's what you got to start with. You have to have something that you can test to tell you what anxiety is in these students. In our example, how can we quantify that? How do we measure that? So consistent observing of behavior, and we can change things to see the change in thought and behavior. We'll talk about how experiments are set up with those changes, but we have to be able to observe behavior and then change something in that environment to get a quantifiable result. So let me put the notes up here. You can pause the video and write these in your own words. Feel free to shorten and shorten this up when you write. All right, let's move on to the next slide. There we go, instinct or data analytics. So we're going to talk about types of experiments. A correlational study is what we're going to run into a lot in this course. Try to see how two factors are linked together, and that's going to be a big part of what we do. But correlation does not equal causation. So just even if we find a link between two variables, it doesn't necessarily mean they cause each other. So like smiling and happiness often come in tandem. They are correlated. When you smile more, you're usually happy, right? So more smiles, higher happiness. But they may not cause each other. The cause is rooted in emotion, in mood, in experience. It's rooted in something else, right? You're not happy because you're smiling more. So they don't really cause each other. So I'll show some examples after the slide, or later in the course here. Often correlations don't account for the cause, which can be rooted in emotion and in mood. So correlations don't necessarily tell us what the cause is, but it shows us if we have a link between things. Cross-sectional studies look at a specific group and studies them. So we might have a cross-sectional study of males 16 to 24. We have a cross-sectional study of elderly people between 70 and 90 years old who are college educated, right? We can have some more specifics about these groups. We can combine multiple cross-sectional studies to get a broader look at the population as a whole. So it can take a lot of time, but it'll be more valuable and more valid. Longitudinal studies observe subjects over a long period of time. So you might start observing them as babies, and you'll observe them for the next 30, 40, 50 years to see how things change over the course of time. Surveys, naturalistic observations, they can all be used with scientific accuracy. We might survey a group of people. We have to be careful about how we survey people, what we ask. Some we'll get into later. Case studies are a deep look at one or two cases. So it can have anecdotal evidence. So sometimes if you only look at one or two cases, then that could be an outlier. You don't know. We'll talk later in these notes about validity, making sure things are valid, but it can give you a real deep insight into a specific extreme case. If you have a disease or mental illness that's very rare, then really digging into one or two people that have it can teach you a lot. So let me put up the slide now. Once again, write these down in your own words. Pause the video, continue on. So experiments groups, you have to experiment to see if your hypothesis is accurate. And so if we have a hypothesis that zinc reduces the time of the common cold, we have to experiment. We have to find out what that is. So we're going to have two groups when we experiment. We're going to have the experimental group, aptly named. That's the group that receives the treatment. We're going to have the control group, which doesn't receive the treatment, right? So in this case, the experimental group will receive the zinc, the control group won't. One of the big issues with this is the two groups shouldn't know which group they're in because they may act differently depending on what group that they're in. So how can we do this with a drug? You can use a placebo, basically a sugar pill, to replace the drug to test the control group. So we're going to give the experimental group the zinc, and they have the group that has a cold, and we're going to give the control group the placebo, group that has a cold, and we'll see. Sometimes what's called the placebo effect comes into play. If that giving them the placebo could effectively reduce certain things that it doesn't actually do anything, but they think that it does. So there's many studies done. If I gave you, you were in pain, and I gave you a pill that was a placebo and told you it was a painkiller, you're actually more likely to say that your pain has gone away. That depends how severe the pain is and where it is and what kind of pain that they attributed for that. But if you have a normal headache and I give you a placebo, it generally will take away your pain, quote unquote, even though it doesn't do anything, doesn't have anything in it. And so that's something that can happen that you have to be weary of. Ideally, a study is going to be double blind. So not only do the participants, they're not allowed to know which group they're in, but the scientists that are carrying this out, they also should not know which group is which. They shouldn't know if they're actually handing a real pill or a placebo. They may act differently. This helps the experimental administrator not favor one person, one group, or overanalyze. Watching people, you don't know. You just kind of think that everything's real or not real. You don't know which is which. So this is happening right now. It happens with like vaccines. When they have vaccine trials. So same thing, like one group will get kind of a placebo vaccine, one group will get the actual vaccine, have to see, which does it actually work more. That's a case. So that's experiments in groups. Here's the card. This video takes some time, write in your own words. All right, we're going to move on to statistics and graphs. And so there are different ways to graph statistics, and I have a couple of them here. Some are better than others, depending on what you're studying, depending on what your needs are. So the first picture I have here is a bar graph. The next one is a histogram, and then we'll talk more in depth about scatter plots. Those are kind of the three big ones for psychology. Bar graphs show categories that increase or decrease in values. So you can kind of see it goes up as time goes on, right? So we're kind of looking at an increase in value over time or over our groups. So histograms are probably what we'll use the most between these two, because histograms are similar, but they are used to provide data for different groups. And that's used really often, because usually we're studying different groups of people. And I'll show you an example after the slide. So they'll use what's called a frequency distribution. It's the number of times someone does something in each group. We're going to test it. So you see the histogram up on the screen. On the left side is frequency. So if we're looking at people ages 20 to 30 did something twice, 30 to 40 did something 4 times. So that's what we're kind of testing. It doesn't go up or down, in just one kind of line. So finally, scatter plots will be a major focus for us, like I said, and it can help explain correlations between variables. So it helps give us that correlation, not causation, but correlation. So we'll go more in depth in a bit. When we get statistics, there are 2 ways that data can be collected and used. We have one way, which is descriptive statistics. That's kind of using the numerical data to describe. So it doesn't really tell us anything yet, but it just gives us the what, not the why. So we have the statistics. Okay, here's what the stats are, and I'll go through an example in the next slide. Inferential statistics is taking that data and determining the probability of it being true of the population study. So that's kind of trying to use the data to explain something. What could be the reasons why? So let me put up the slide once you write this down, and then once you're done, we'll take a look at a histogram example. All right, so here's a histogram example. So so what we kind of see with this is the descriptive statistics, right? This is the descriptive statistics. We've taken the data, we've broken it down, and as you can see, we're charting the frequency of trees within a certain height range. So how many trees do we have between 100 and 150 centimeters? We have 4-ish. Between 150 and 200, we have about 30. So that's kind of the data. We have 50 trees between 250 and 300. That's our highest. This is the descriptive statistics. For the inferential statistics, now we're going to make inferences, things that we don't know what's true, but we could take some guesses based on logical proof. So perhaps the taller trees are older or have more consistent sunlight, so they're taller. So maybe they're better taken care of, right? So this is where these kind of fall in. Because we have more trees that are 250 to 300, maybe there's certain things about those that we can determine. So, all right. So continued. We're going to keep talking about this, and we're going to talk about scatter plots specifically. In scatter plots, we can determine the correlation between the 2 variables we're testing. We can determine the strength of the correlation with what's called a correlation coefficient. So a plus 1.00 is the best positive correlation. That's the max. And a negative 1.00 is the best negative correlation. So the closer you are to that, the closer these things are correlated. Once again, doesn't mean that they cause each other, but the closer to that high coefficient, the more that these are correlated. So if age and income have a correlation coefficient of 0.7, that means the older you are, the more likely you are to have a high income. That's pretty good. 0.7 is a pretty good coefficient, right? Because it's close to 1. Basically the lowest in terms of not having a good correlation would be 0. So 0.7 is well above that. If the weight of your car and the gas mileage has a negative 0.6 correlation coefficient, then the higher the weight of your car, the lower the gas mileage of the car. So that's fairly well correlated. So these positive correlation coefficients have positive skews generally. So you can see that down here on the right. A right skew to positive skew for kind of the positive correlations. And we'll talk more about that in a bit. And then negative correlations have kind of a negative skew. They drop off at a certain point, as you can kind of see with the graph. And so that's a little bit different, but most of the information is on one side of the graph. That can happen as well. A bimodal distribution has two peaks, so it's kind of two hills with two valleys. We'll dig more into that later in the course. Let me put up the notes here and get that going. There we go. Sorry about that. So you can write this down in your own words at this time. So here's some scatter plot examples. You don't have to draw, but you can reference this back. The positive correlation could be something like height and weight. So it's not perfect, but it's moving up to the right. So that means that the taller someone is, the more they weigh. Those things are correlated. Once again, they don't cause each other. So as I gain more weight, I get taller? No, right? So you got to watch yourself. But this is a positive correlation. Not every dot is on the line, but it's pretty close. And depending on how close they are, that's where our coefficient kind of comes into play. The negative correlation could be something like age of a car and price of a car. So as the age increases, the price decreases. So that's a negative correlation. Those are going in opposite directions. So it moves down and to the right. Then on the right, we could have IQ and shoe size. It's not correlated because they're all over the map. Some people with more IQs have bigger feet, some have smaller feet. Some with lower IQs have bigger feet, some have smaller feet. So that's that. Correlation is not equal causation. I'll say that more times. You'll get sick of. We cannot determine which variables is the cause without some type of study. As I said, does being taller increase your weight? Does weighing more increase your height? Are neither of those things true? Just because we have a correlation doesn't mean we have found a cause. We need to experiment to figure that out. So here are a few examples of correlation not equaling causation. So I think these are some funny correlations that work. So the number of people who drowned by falling into a pool a year correlates with the films Nicolas Cage appeared in. So the more, is it like every time someone drowns, Nicolas Cage just pops up and says, I have to do another movie? No. Every movie that Nicolas Cage is in, someone decides to die in a pool. It doesn't work that way. And this correlation coefficient is 0.66. It's decently strong. That's pretty strong. So they correlate pretty well. They don't cause each other. They have nothing to do with each other, but we can still say they're correlated. This one's fun too. The letters in the winning word of Scripps National Spelling Bee correlates with the number of people killed by venomous spiders. Once again, is it that every person bitten by a spider, the National Spelling Bee says, hey, add a letter to the last word, or the longer that word, the spiders start coming out? That's not how it works, right? The correlation is not equal causation. This coefficient is 0.8057. Very, very strong. It's very, very close. So that's a problem. So that's why we got to keep in mind, hey, even if you think you know, you don't necessarily know how correlation causes causation. So, all right, let's talk about statistical terms and kind of get into some of the stats and data. Once again, hopefully this is stuff that you've had before, ultimately, but we'll kind of get into it here. So This is a major part of the FRQs as well on the AP exam, because you're going to have to take data, you're going to take correlations, you're going to have to analyze and interpret that data. So when we have data, we want to find these central tendencies. Basically, what is most of the distribution located in the middle of the graph. So if you look at this graph down here, we want to find where's that middle, where's there most people falling into this this kind of data that we're getting. We must be able to calculate the central tendencies of data. So there are different ways to do this. We can find the mode. The mode is the most frequent occurring score. We can find the mean, which is what we colloquially call the average, right? Find the average score. We can find the median. What is the middle score in the distribution, where half of them are above, half are below? What's the range? The range is the lowest score to the highest score. And then the standard deviation. Now, you do have to know how to calculate those first four: mode, mean, median, range. You can do all those without a calculator. They're all very easy. We'll go through it. Standard deviation, you don't have to know how to calculate it. It's the square root of and you don't have to be able to calculate that. You don't have to know how to do that in your head, but you do have to know how, that it's a measure of how scores vary around the mean. I'll get into that as well in a little bit. So you can at least know what it is, and know if you see a graph like this or have scores that make a graph like this, how you can tell what that standard deviation is. So let me put this up for you to write down, and you can pause the video and write this down at this time. So here's kind of an example of a normal distribution, and this is basically like kind of a normal bell curve that you might see when you're getting data. Not every bell curve will be as normal as this, but it can work. So as you can see, we have up here labeled the standard deviations of 1 and -1. So one standard deviation away from the middle, both positive and kind of negative. So about 68% in a normal distribution, 68% of your data will fall in the middle. And you'll have one standard deviation to the left, one standard deviation to the right. If we add in these standard deviations, we should have about 95% of our data there. So that's 2 standard deviations. And then if we add in going to the third standard deviation, and we're going to have 98.5%. We're going to have almost everything within those. So if you see something that talks about standard deviation, know, hey, okay, 68% falls within the middle. We will have 95% fall within 2 standard deviations, and that way you kind of know. So, so this is distribution of pizza delivery times. So most pizza is delivered at 30 minutes, and between 25 and 35 minutes, most pizzas are getting delivered, 68% of them. But we have some that are between 20 and 25, some that are between 35 and 40. So that's 95% are going to fall in there. We got a little bit of outliers here, 15 to 20 and 40 to 45. And so that's going to be 98.5%. And then there's those, 1 or 2 that take forever because they get in a car accident, or, they live next door to the pizza place. They can just walk it over. So that's a normal distribution. So let's look at a data set as well. And you don't have to necessarily write down this example, but you can. Or if you know how to calculate these, it's great. So just try to do it in your head. The data set 32582. So we come up with that data for our participants in the study. What is the mode, median, and range? So the mode is the most frequent. So that is 2, right? Because we have 2 2s. Everything else is just 1. So the mean, if we add them all up, we divide by the total number. So add them all up. We get 20 divided by 5 is 4. The median is kind of the middle number that has the same amount behind it and after it, and that's 3. Right? So we have 2 2s to the left of 3. We have 5 and 8 to the right of 3. So 3 is the median, and the range is our smallest to largest number, 2 and 8. So you have to be able to calculate those on the AP test. These are really the only calculations you'll need to do. So something to note. Now, let's talk about variables here. When you set up an experiment, you must have a factor to manipulate, which is called the independent variable, which on the slides I'll put IV when we use independent variables, so you don't have to write that out every time. So we have to have something to manipulate, something to change, and that's the independent variable. And then we have to observe the effect of that change on behavior or mental processes. That's the dependent variables. Hopefully some you've had in science, but just to reiterate, independent variable, dependent variable. So FRQs, multiple choice, they're often going to ask you to identify these. So this is something really to know. They'll give you a study. What's the independent variable? What's the dependent variable? That's important. So if we wanted to see if flashcards helped with test scores with kids in elementary school, the flashcards would be the independent variable. Right? This is something we're going to change. We're going to have a group that's looking at flashcards and studying, and they'll take the test. We have a group that doesn't, and they'll take the test. The test scores are the dependent variable, the dependent variable. So the test scores is what we're observing. That's what we're testing for. And so if we see the flashcards, the kids who use the flashcards consistently have higher test scores, then maybe we could say this is something that is viable. Is something that's correlated. We can do that. So there's our flashcards. So let me put up the slide. Here's the slide. You can write this down in your own words. Pause the video at this time. So hopefully it makes sense. We'll look at some other variables as well, because there's a lot of variables that can confound or skew your results. I mean, a lot of things can make the results of your study not work. That's something you have to be able to identify when you look at a study. Now, if there are more variables than the independent variable, this can be problematic. We really want a study where just the independent variable is changing, nothing else is changing. These are called confounding variables. So any variable that could impact the results of an experiment, we have to make sure they don't confound our results. So examples could be age, sex, health, attitude, personality, socioeconomic status, intelligence, etc. If any of those things are skewed, then our study is not going to be valid. So, for example, if we want to try and see if money buys happiness for the general population, so we're going to bring people together, we're going to survey them about money buying happiness, but all of our subjects are millionaires, all of them. It's going to skew our results, probably. It just might. Maybe they're going to have a different feeling. Or, if all our subjects are men, it's going to skew our results. Or if all the subjects are 60, 80 years old, it's going to skew our results. So we have to, unless we want to get information just on that group, then we have to make sure that we account for those confounding variables and keep it even. So we're only testing a specific population in those cases. We don't want to do that. So we need to eliminate confounding variables by turning them into control variables and being able to manage them. So we can make sure we have equal of both genders, right? We have men and women. We can test a specific age range. Let's say we just want to test people 60, 80 years old. Great. We can make sure we just have that group. So, I can even do both. I can test 16 and 24-year-old men and know that my results just come from that group. That's where we get into the cross-sectional studies. That's one little cross-section that we're looking at, and then we can test others. So let me put up the title card here, and you can take a look at the other variables. Let's continue on to significance. And The fewer confounding variables, the more statistically significant a study has. The more statistical significance it has, and the more probable your results are. So, if we don't have confounding variables, we can say, hey, our data, our experiment, it's valid. It's the probable these results are right. You want a pure experiment if possible, so the results are significant. So that's what it's called, a pure experiment, if you don't have those things. And if you follow the procedures to have few confounding variables, you'll have pure experiment. That's why you should be skeptical just seeing a study says this. Well, what are the confounding variables? What are there problems with the study? I think now you can kind of dig into some of these studies, whether it be about health, whether it be about mental health, whether it be about a certain group of people who does this or believes this. Who are we testing? There's other things to talk about that can be problematic. So let me put up the slide. All right, so you can write this down at this time in your own words. Let's talk about assignment and selection. One of the confounding variables can be the selection and assignment of the study. So you want to choose people at random for your study and assign them to your groups, your experimental group, your control group. This is random selection and random assignment. So the selection needs to be split into two groups. Like I said, the experimental group, and that's going to be the group that the independent variable is changed to see if it has an impact. And the control group, which is kind of the normal baseline group. So we want to randomly assign our participants. So let's do an example. Let's say we want to test the effect of fear in children. Our hypothesis is that if babies are exposed to fuzzy bunnies at the same time that a loud cymbal was struck close behind them, they would fear all fuzzy things. Another group is exposed to the bunnies without the cymbals. Now I want you to think for a second, what is the independent variable in that study? What are we changing? That's the one that's changed, that's manipulated. So it would be symbol or no symbol, right? Are we crashing the symbol or not? That's the independent variable. What's the dependent variable? What is dependent on that? It's not the fuzzy bunnies, but the response to the fuzzy bunnies. We want to see fear. So we would have to define that and define how we're going to gauge that. But because that's what's impacted, right? The fear is what's impacted, not the bunny, the independent variable. So just something to keep in mind that the dependent variable is what response we're looking for. The experimental group is the group of babies hearing the symbol, and our control group is the group that has no symbol. So hopefully that makes sense. But definitely ask clarifying questions if you need to. I'm going to put up the slide. All right, so let's go to validity, and hopefully we'll get, this will be our last slide here. We'll talk about getting valid results. Hopefully your results are valid. The larger the sample size, the more reliable the results. We want a lot of people in our study. So if I randomly select and assign two groups of 1,000 people each from various neighborhoods, the odds of me having substantially more males to females or substantially more people of higher intelligence and lower intelligence are extremely low. If I select 10 people, then my results could be skewed. What if 5 of them have high intelligence and they're all in the same group? They're all in the experimental group. That could throw off my study depending on what it is. So be skeptical of studies. Be skeptical of studies with only dozens instead of hundreds or thousands of people. That's a big problem. I mean, there's a lot of studies that are put out there that have 24 people studied. That doesn't help us. That doesn't tell us anything. But if we have thousands, we can take those outliers aren't going to impact our data as much. So it's a lot tougher to control for our confounding variables if we have a lower sample size. So you want a big sample size to make sure that we have that. So let me put up the slide. You can write this down in your own words, and after that, we're done with Notebook page 3. We only have one more page for this unit, and then we have the first unit done. So this is an important one that you just watched. It's important for the FRQs. It's important for the multiple choice. It's important for the data collection and the experimentation piece. We'll do some work practicing this. So hopefully you enjoyed the video, and I'll talk to you all soon.